Your video is not active right now.
It should be now. Oh, the video's not active? Yeah.
No, so you're the one where you have the video on is muted, and the one where you don't have the video on is.
Thank you. Thank you. Just a second. I'll fix these things. Turn that off. And okay, everybody hear me again?
Yep.
Okay, this is what's normal. In order to show you the video, I had to switch some things around. So I suppose you can see me now?
Yep.
Okay, and we're recording. Anyway, I can show you lots of things. I've got like 600 hours of African animals and all kinds of things charging us and so forth. Those things are things you'd like to see. Most students, if I ever show a student that, they always vote for the animal, always root for the animal. Anyway, okay. Well, since I had this open, I'm going to go to the screen I had a while ago that we were playing with. For some of you who came in a little bit later, we were looking at some pixelated pictures, and you'll see those a little bit again, maybe. Okay, where we are is going to be in the notes today, but what the book is doing in the same area is essentially chapter 14. And in 13, he does curves. All this will become clear pretty quickly. Anyway, if you look at section 14, chapter 14, section 1, he says functions of several, of two variables in this case, but above that it says functions of several variables. And for him, when he says that, he's talking about a function which starts out with like an x, a y, and a z maybe, and gives you something else. In other words, a formula might be, I hear something making audio noises, don't know what it is. If we write y equals f of x, then the x and the y are both real numbers. That's called a real valued function of one real variable. On the other hand, if we say f of x and y is equal to z, that's what he's doing here. And when he says z is f of x, y, when he writes this stuff right here, he's, where is it, up above here? He's talking about a real valued function of, in this case, two variables. So his t is like what I would write as z. So if you had a formula, you might have x squared plus y squared. That would be the right-hand side. If I set t equal to x squared plus y squared, that's an equation, three variables, but we have one variable solved for the other two. So we call that a function of two variables, or we make a function of two variables from the equation. Now, what we're going to do shortly in the notes is the thing I have my finger on instead of x and y is going to be like x sub 1, x sub 2, x sub 3, maybe the x sub 50 or x sub 5,000. In other words, we're going to have the ability to have more variables here. And the t may also become a vector, because maybe what we want to do is compare a vector to a vector. It might have a formula that takes a vector, which is several variables, and gives you a formula that tells you the several other variables. We'll have examples of this. But for the book, he's doing real valued functions of a real variable. Okay. Chapter 13 is doing vector valued functions of a real variable. I think what I said a second ago is wrong. He's doing real valued functions of a vector variable in chapter 14. Chapter 13 does vector valued functions of a real variable. I wanted to try to explain vector valued functions of a vector variable so we get both 13 and 14 in terms of functions at the same time. So we don't have to spend time later going back and having to say, well, now we have to start over again. By doing it in general first, it takes care of the specifics of both chapters later. So anyway, but if you want to read some stuff, and I'm probably going to put some problems on WebAssign, what he's doing is either two variables or three. And when you have a function whose domain is two variables, then and the range is one variable, you can actually make a graph of a surface of that where you put the two variables on the floor. So if you have a region on the floor, and for each x pair xy in the region, for each pair xy in the region, above it you have a z, and that's a height. And when you put together the pair of numbers on the floor together with the height, you get surfaces. And his picture of that is down here in where he's talking about a domain, which is two variables, and a range, which is one variable. You put the two together with the one and get triples, and those form a surface. So we will be talking about that later, because once we do m to n or n to m variables, then we just let the range variable be one, and then we've got these kind of things. Now, if the domain is more than 2 dimensions, we have a 3-dimensional domain, then the domain will be a solid of some kind. And the range would then be something, maybe temperature or time or some other fourth number, but we can't see it in a picture because we can't graph 4 dimensions. Okay, so we'll have other ways of putting dimensions together when we can't really see putting the domain and range together. Anyway, but you can look in here and get some ideas of various pictures and various things that he puts together. These are real valued functions that give you surfaces when you graph them. And they're kind of interesting, some of them. These are things that you're not going to be expected to do yourself. But he's just writing down some examples of some functions of 2 variables. And you can see that, you know, the things we might be able to study mathematically with such ideas. He then goes into the idea of level sets or level curves. And the thing you got to remember for a level set, if you think about this right here, it's not these curves up here on the graph. The level set or levels curve is down here on the floor. It's the x's and y's, the pairs, that give you the same height. And if I look at this picture on the floor, before I've graphed this space vehicle on top, if I look at the things down here and I mark what they mean, that's the range variable there. That's the f of xy. And what we're saying here is that everything on this curve goes up to the same height, and it helps you graph the solid because, not the solid, the surface, it looks like a solid, but the surface, because for you, if you know that this thing is going to go straight up, it's sort of like intersecting it with a cylinder to see what the thing is up here, and that would help you graph it. So people stare at such things, for example, topographical things. Any of you who walk around in wilderness areas or whatever might be wise to carry a map with you, which tells you about the altitudes that you are as you're going a certain way along here. You know, if you, for example, follow this path, it may not be an actual path, but if you follow along here, you might have an altimeter with you that's telling you what the altitude is. If you stay at the same altitude, you're drawing a level curve, which 3-dimensionally, if you graph that as a number above, you actually will get a picture like this over here. And so this is a 2-dimensional picture of the mountain. Okay, sad because it's called Lonesome Mountain. That's kind of a sad place. But anyway, he then shows you other kinds of pictures and stuff. You guys can look at these. I don't want to spend more time on that. But we're used to seeing, because we can't carry 3 dimensions around very easily, when we're trying to see a map is sort of a picture of the 3-dimensional region in 2 dimensions. And that's utilizing these ideas of level surfaces. The other thing we do with these things, and he shows you some more here, these are all level surfaces. If you see these level surfaces, that's supposed to tell you what the graph looks like. Sometimes you have to be really clever to see what it looks like. But for example, you know, these pictures here are supposed to show you the stuff over here. And you can stare at them a while and see if that helps you. we also use what are called sections. And so I've run out of pictures here, but sections basically are where you slice the surface with a vertical plane. And you look and see what the graph looks like that you have sliced. In other words, what's the intersection of the vertical thing, like the knife you slice, what's the two-dimensional picture you get when you slice, okay? We'll be talking more about that stuff. Anyway, so section 14 is basically getting you familiar with the idea of functions of several variables, so-called. And when you get to chapter 15, that's, I'm sorry, not 15, 14.2, that's when he starts talking about, you see over here the name, hopefully, if it comes into focus, limits and continuity. So what you and I are going to be talking about the rest of the day now is some notes I have, which I put on the Blackboard, which I hope you've had a chance to at least look at, if not study. We're going to be talking about limits and continuity first, okay? Now, we're not really in chapter 14 because I'm trying to do something more general than either 13 or 14. And so I'm going to put up another screen now, which presumably is what I want to talk about. So I hope now you see a screen about limits. And what's above here, this is page 3 in the notes. What's above is me developing notation like this. When you see something like this with an F like this, this is saying I have a function that goes into 3 dimensions. The author in chapter 14 is not talking about that. He talks about this idea in chapter 13, which we'll get to. So if you have a function from n dimensions, you don't see any evidence of that here. What you see here is into m dimensions. When you go into m dimensions, you will have m functions, and the m functions, each of these is like the ones in chapter 14. In other words, f1 will take n dimensions into 1. f2 will take n dimensions into 1. You don't see the n dimensions here in this picture. I tell you here it's 2 or 3, saying the domain, when you say 2 or 3, that tells you what you have in terms of domain variables. This is the range. It's the space you go into. So we'll be talking more about that. But the first 2 pages are just trying to get you used to notation. And then we come up with this definition here. Now, what I'm going to do is go off this page real quickly here because I want to write some stuff here. But what I'm going to write has to do with repeating this line right here. And this is a line I hope that you saw before in Calc 1 or Calc 2, at least something like it. What you didn't see before is double lines here and double lines here. What we're talking about is limits. Now, this is what you usually see, but again, what you usually see doesn't have bold face. Usually the X and the X naught and the F and the X and the L are all just normal, like this right here. You don't usually see it like bold. I use bold in print to tell you this is not the same as this in Calc 1 or Calc 2. I use a bold F if we're going into multi-dimensions. I use a bold X if we're coming from multi-dimensions. So anyway, this is the definition of limit. So I'm going to go off the screen now, if I can get off of it, and go over to the other screen, which is, what screen is this? It's not that one, this one. Okay, so what you should see now is a clipboard. All right, so if I say the limit, let me take this, okay. Hopefully the screen will adjust to this. If I say the limit of f of x equals L, Okay. You're used to seeing things down here like this. And I know you're used to seeing something like f of x equals x squared. And so you're used to seeing things like what I'm going to write here. You're used to seeing things like this. I notice it's a shadow now because I was trying to play around with those pixels earlier. Anyway, this is what you're used to seeing, is this kind of a line right here. What some of you may not have done before is prove something like this is true. Now, so there's a definition, and when you first start out doing limits, you have to prove stuff using that definition. Then what we do is we get tired of that. Hopefully you learned it first, but anyway, we get tired of doing that kind of proof. And so what we do is we start thinking about proving things in general, more abstractly, about functions for which we don't have formulas. But we say, like, this is looks like I squared things. I could write this as the product, x squared I could write as the product, and I might wonder if I could split up stuff. All right, maybe I can split things up and make this a product. Why would I do that? Because this one might be simpler. So maybe I have to make a proof of this one and see what its answer is. And I also have an abstract thing saying, if I know what these two limits are, I can multiply them together to get this answer. So as we go forward, at first you have to prove some stuff with what we call epsilons and deltas. Then hopefully you develop some theorems, which for later things you don't have to prove directly with epsilons and deltas because we use theorems to prove. Now, is that kind of clear as to what I'm trying to say here? Because we're going to do exactly the same thing, except over here, I'm now going to put a bar under the x and all these things. If I put bars under them now the thing I'm squaring out here, that no longer is applicable because, for example, you can't take a vector and square it. Okay, so if x is a vector, the x2 doesn't make any sense anymore. But the definition is similar. So let me write down the definition now of what do we mean by this situation we had before. Some of you may have seen it, and this is going to be sort of symbolic, and that may not make much sense to some of you for a few seconds until I try to explain it. So I use an upside down A, and so does every other mathematician ever born, for at least since the 1880s, for the words for every, for all, for any, for each. It means all, everything, all things, excuse me. And this says for any number that's positive. It's called epsilon because we use Greek letters to do this. Epsilon's the fifth letter of the Greek alphabet. Delta is the fourth letter of the Greek alphabet. This says for any number that's positive. There is, this backward Z is called an existential quantifier. It means there exists. So if I said to you this on a telephone or with a video off, you couldn't tell I'm using symbols because I just write it in English. If I wrote it out, it would be for every epsilon greater than 0. For every number greater than 0, there's another number. Could be the same, could be different, don't know. There's another number greater than 0. And then I might write out such that there's also symbols for that too, but I don't want to give you too much problems. So for every one of these, there's one of those. It's like for every comedian, there's a crowd. Okay? For every politician, there's a lie. Anyway, maybe my last day. For every number, positive number, there's another positive number. So this number is going to be associated with this number. So for every one of these, I got one of these. I may have more than one. There exists means at least one. So for each one of these, there is one of these or more, such that. Now, next is another one of these. For everything in the domain. So now I should have already spelled out what the domain of the function is. That ought to be done before we start. So I'm going to go up here and say, I have a function whose domain is D, whatever that is, and I'm going to go into M dimensions. And since I said D, I better tell you D is a subset of N dimensions. Now I've tried to tell you a name for the domain, which I should have done first. So now that I know what the domain is, what am I asking? I'm taking an X in this set. Now, back here on this thing up here, sometimes people don't write down the domain. You guys know that. That means sometimes they tell you you can use any X that makes sense. And in this particular function, if nobody tells me different, I would be assuming it makes sense for any real number. So the domain here would be R, the real numbers, or E1, which is another name for R for us. Anyway, this says for every epsilon, there's a delta such that for any X in the domain, okay? So for this function up here, by my right thumb, that's any real number, okay? Then we have an if-then sentence. And the if says if 0 is less than, it looks a little complicated. Okay. The next thing.
We can't see what you're writing right now.
I'm sorry?
We can't see what you're writing right now.
Thank you. Thank you. When we take limits, okay, we are talking about heading towards something. We're talking about getting near, actually not heading toward, but the notation make it look like X is heading toward. Actually, what we're doing is getting near to something. So in the problem I have, this problem right here, this would be -3 right there. If I have X naught up here, then this should be X naught right here. So I'm going to put X naught, okay, and I'm going to put a bar here, but we'll get to that. Anyway, this is where the place you're heading toward is put. And what I've now spelled out is this says the distance between the X I picked here and the given X naught I'm heading toward, the difference between them, that's distance. The distance between them is smaller than this number. And I'm picking something that's not X naught. I'm picking an X in the domain, which is not equal to the point I'm heading toward. That's what that says. The distance between them is positive, meaning they're not equal. The distance between them is less than delta. That says how close they are to each other. And if then sentences have thens, and that says that f of x minus L, and again, I'm getting off the screen, I see. Which way does it go? Is less than epsilon. This says that f of that x I picked, its distance to this number L that I'm claiming is the limit, the distance between them is less than epsilon. For the problem we had at the beginning here, what we have if I graph it, now part of the reason for doing limits is because I don't know what the graph is. But if I graph this x square thing and I go out here to 3, from what I'm saying at 3, f of 3 is 9, and so this would be the point 3, 9. What this statement is trying to say is when I get something close enough to 3, in x close to 3, f of x is close to height 9. That would be what I was doing with this function up here. And this thing in the middle is explaining that. Now what it says is epsilon in this picture would be a little distance around height 9. And the delta would be a little distance around 3. So what it's saying is, you decide how close to 9 you want me to get. I will tell you by picking delta how close I need to be to 3 so that anything I pick inside that distance will map up to your prescribed distance of 9. This has to do with target shooting in a sense, because we call the things you get the range. Those are the things you might hit. okay? And so the word sometimes, I use the word target also in this scenario. And so what we're talking about here is being a good shot, being a good aim. The function is actually going to hit the thing, but that's called continuity. We'll get to that, okay? First is limits. And now, I put a bar under here. I said I'll get to that in a minute. If that's what I'm doing, then some of this doesn't make any sense. Because for me, distance between vectors involves norms. So you would see that, and you'd see an arrow under here. You wouldn't see an arrow under delta because delta is a number. If my L is a vector, then I need to have bars under here, and I need to have two lines here. And I just changed from one dimension to one dimension into n dimensions to m. Now, this norm here is in n dimensions because that's the domain world. This norm is in m dimensions because that's the range world. So sometimes we will put an m and an n in extra to tell people. You won't see that in the notes, or you won't see it in the book at all. But sometimes people want you to know that these two lines things, they don't mean the same thing. This is the square root of the sum of squares of n, like 5. This would be the square root of sum of maybe some other number, like 7 squares. So now, when we're all in real numbers, then this is absolute value and this is absolute value. That supposedly is what you've learned already. What I hope that you will feel is, since you really studied this in Calc 1, it's now easy. Now, if you don't feel that way, if you didn't study it, well, you thought you escaped because you passed. But you didn't escape because I'm going to hit you again with it. Okay? So this is a definition. Now, how do we use the definition? We use the definition on some simple functions, not complicated functions, thank goodness, because none of us are that good about manipulating. What we have to do is find a delta for an epsilon. We don't know what epsilon is. We have to find a delta somehow, and I'm going to show you how to do that, and that's in the notes too. But let's just take an example, and in a few minutes, nobody else is showing up. Maybe I'll do that right now while I talk. I will, if I can find my thing. I will take a picture of you guys. Maybe I will show gorillas in my picture. I'm just playing now. This is what shows up in the capture screen, see? So I'm curious again as to what happens when I take a photograph of this. So may as well do that. Okay, so you are now immortalized, and I can take the mother gorilla and her son away. Okay, so let's talk about a nice easy function. Let's talk about a constant function. So f of xy is going to be, say, 2, 3, 4. Now, I'm going from 2 dimensions to 3. So really, it's better if we would write this as 2, 3, 4. Book publishers don't like that because it takes too much space, but that's more correct. So really what I really have here, now I'm going into 3 dimensions, so I ought to have a bar under f. So this is a function from 2 dimensions to 3, and it's called a constant function. Now, you're used to constant functions like 2, and you graph it, you get a horizontal line. Okay? Everything's at the same height. Well, everything's at the same height here, except the word height becomes rather strange when I'm trying to talk about something from 2-dimensional domain and a 3-dimensional range. That's a 5-dimensional picture, which, unless you are on certain drugs, is hard to understand. And I hope nobody ever does that to you. Anyway, what do you think the limit as the function as f of xy, xy approaches something, I don't know what, -1, 4, say. And by the way, what's the domain of this function? If it's a constant function, it doesn't matter what I put in here, you get the same answer. Therefore, the domain would be all of E2, all of two-dimensional space. Or some other subset, but if I don't see anything else, I might say it's everything. So I just picked something, -1, 4. What happens to the function? What do you think happens as you approach this number to this particular function? Now, I called it a constant function. I think it's not going to change anything. I think no matter what I put here, no matter what I approach, I'm going to get this answer. That's what the formula says. How would I prove that? With epsilons and deltas. To prove an epsilon delta statement, you take an epsilon, take one, and I have to next choose the delta that goes along with it. Now, the problem with this particular function is it's so easy that it's hard. Meaning, you always have to worry about how you pick the delta. But this is such an easy function, I'm going to pick the delta to be 5. I'm just making that up. Because we're going to find out it doesn't matter what you pick. Okay? So I chose it. In other functions, I'm going to be more careful than this. This is like saying, I'm a good shot. If you stand within 6 inches of my shotgun, I'll be able to hit you. Well, anybody could do that. You don't have to be a very good shot if that's all you had to do. I hope it's never something you have to think about. But anyway, I tried to pick, or even more, if you're standing in front of my cannon or my nuclear device, whatever. What is the limit of this? Well, what you do next is you have to pick something in the domain. In this particular case, that could be anything. So I pick anything in E2, and I assume that the thing I pick is distance from -1, 4. So I'm going to write it out here. I'm running out of room on my page. I'm assuming that the distance between them is less than 5. So I'm getting within, so the domain I picked is the floor. So for each point on the floor, I have the value is 2, 3, 4. Now what that could be, for example, could be the temperature, the humidity, and the, I don't know what, the altitude. 3 numbers. Okay, so at each place on the floor, you might have those 3 numbers attached to that place on the floor. Anyway, I'm going to assume that I'm within this distance, 5, of, I picked an xy that's in that distance. And I have to figure out what f of xy is. What is f of xy? And what is the limit? The limit we said was just 2, 3, 4. But what is f of xy? F of xy is 2, 3, 4 because it's always 2, 3, 4. So what do I have to prove to show you it's true? I have to prove that this difference is less than epsilon. But this distance happens to be 0. And 0 is less than epsilon. So the point is, I found a delta that when I stick this stuff in the if, then, and all that, it actually worked. Okay? So now I'm going to get off of this, and it's also 16 after, and go back here and try to show you the next 30 pages in 4 minutes. Okay. I joke sometimes. Okay, so now what you'll see here is this is the same thing for f of x equals c. A minute ago it was 2, 3, 4. Here's the same proof for constant functions. But the difference is on the paper a minute ago, I did it for one particular constant function. This does it for all constant functions. So what you try to do is do things in general so you only have to do it once. If I had to do it for 2, 3, 4 and 1, 7, 9 and so forth, and then different dimensions, I'd be doing it forever. Okay, a little bit harder function. what if I have the identity function? Now, the identity function says f of x is x. So I make a proof. Again, I believe that when x has the x naught, f of x is going to have the x naught. That's what I believe. So to do limits, you have to decide what you think the limit is. All right, and then you prove it. So here's the proof. Now we're running out of time, but again, in this case, the delta wasn't anything. I could get away, I found out, that the delta is epsilon. Now, how did I say I get away because I found out? That's because what you do to do this stuff is you go down here as if you already know what you're doing to try to see what this is. When you evaluate this to see what you need. So when I evaluate this for this particular function, f of x is x, L is what I chose, that's x naught, that's the L. So what I chose here to do this is x minus x naught. That is going to be, when I pick the delta, I'm going to assume that this thing right here is less than that. So when I get over here, this will equal that, and that will be less than that. And what I need to do is get this thing less than epsilon. What I do get is this thing is less than delta, but if I pick delta to be epsilon, I've done what I said. Now, you guys can listen to this by going back when it's recorded and hear what I said over and over again. I hope what I said is what I meant to say, but this is a little harder, but it tells you if I already know, this just verifies it. The way I found this out is to go and look at this down here. We're going to practice this on Wednesday. Now, the norm function is also has a limit. That's when the norm of f of x is x goes to x naught. That's just a little bit more complicated. Limits are unique. There's only one answer here that you can make, and they prove they're unique. And then we go into, instead of doing more complicated functions, see, all I did was identity and a constant function. Instead of doing more complicated functions, I now go and try to show you, if I know what the limit of one function is, and I multiply it by 2, I know what that limit is. You just multiply the limit by 2. So this is a proof, very abstract, of proving if you know this, then you know this. Then you get that. Then here, what if I have two functions that I know their limits? And somebody wants to know what's the limit of the sum, determine the limit of the sum is the sum of limits. And the proof, of course, it gets more complicated. So one of the reasons to do this is because it leads you into more complicated situations to solve. And the idea of that is to learn how to do it. So I would ask you to try to understand these things. And to do some of the later ones, we have to do a couple more things about functions are bounded near a limit. There's a couple of things like that. And then we can get into reciprocals, so it's more complicated. The proof is more complicated. See, it's longer. Products, proof is more complicated. This is probably making you dizzy. I apologize for that. This proposition is very important. We'll be using it lots. And then the rest of these, this one's nice because it says if I'm going into m dimensions, I don't have to worry about doing that. I just do m of these. That's very helpful. You'll find out. And there's a couple of more things we do. If I'm heading f of x heading to a, that's the same as the difference heading to 0. So some of the things here on pages 9, 10, and so forth are helpful things, you'll see. And we've run out of time. I'm going to cut the, if I can get off of this screen. I have one thing I want to tell you before you guys all leave me, and I need to get to that. So let me stop the screen sharing.